No. No writings. No. Oh. Okay, don't want a presenter view this time. Allora, let's share the screen. Okay, can you see online?
Yes, we can see.
Okay, good. So welcome back after the Easter holidays, and today lecture we will talk about different representation of orientation, different than rotation matrix. Last time we discussed about rotation matrix, and now we will see the why the rotation matrix are limited in some sense. And the main disadvantages of rotation matrix are, as representation of orientation, related to the fact that they are not minimal representation of orientation. Why they are not minimal? Because they need 9 parameters. So we have a 3 times 3 matrix, and we ideally need only 3 variables to represent orientation. And indeed, we have 6 constraints. We remember that these are the orthonormal constraints that we discussed last time that makes the R matrix an orthonormal matrix. Yes?
See the representation.
Oh, yes. I see. Yeah. So I need to share this way. So let's put on a secondary monitor. Yes. I should do like this. No. Let's see if I manage to write on this. Oh, okay. I didn't know I could do that. I will share again. Sorry. Yes. Now, how can I go forward here? No. Okay, I have some issues with PowerPoint. Sorry about that. Now you see the presenter view, which I don't want. Oh. Okay. 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 So online you can see now the other issue here with the presentation.
No, the screen is not being shared.
Okay. And to reshare this. Okay.
Now we can see it.
Yeah, but here it disappeared. Okay. No, it's okay. So as I said, we have this orthonormality constraints, and if we subtract to the nine variables that we have to represent the rotation matrix, the 6 constraints, we end up with three independent variables. So that's why we need at least 6 degrees of freedom to position the effector and regulate also its orientation, because we need 3 parameters. 3 degrees of freedom to position the end effector and 3 for orientation. And another reason for which we don't want to use rotation matrix to represent orientation is whenever we do interpolation. For example, let's think we want to go from an initial orientation and move to a final orientation with a straight line. So a path, let's say, that goes from the PI position to the PF final position does the job. And for position, you could think about, for example, do an interpolation where we start from PI plus PF minus PI times S, where S is a scalar that goes from 0 to 1. So when S is 0, we have P is equal to PI. Whenever S is 1, we have P equal to PF. Can we do the same for orientation, in your opinion? Something like that? Can we do that? Do you think it's possible to do that? As we did for position? The answer is no. And why? Because in the intermediate locations, so we might ensure the orthonormality properties for the initial orientation and for the final orientation, but for whatever is in the middle, we are not able to ensure them. So this is a limitation of the orientation matrix. Oh. Then the third one is whenever we come to define orientation error, for example, we want to have a desired orientation that we want to track. We have our actual orientation of the end factor, and we want to compute the error between these two orientations. And again, we cannot do the simple subtraction of the desired orientation minus the actual orientation, because again, we have not insurance that is a rotation matrix. I remember we don't know if it will satisfy the property of having a unit vector as columns, the property of having the columns orthogonal each other, so having a scalar product 0, and also determinant equal to 1. So, but we want to have a tool that allows us to derive the orientation error the same way as, and the interpolation the same way we do with positions. That's why we come, for example, to introduce the angle axis representation. The angle axis representation, comes from a simple idea. Think about your starting orientation, let's say your actual orientation and your desired orientation, and you want to compute, you want to know how is the second frame oriented with respect to the first one. And you can think about a generic rotation that is defined about an axis that brings the initial frame to the final one. So given this axis and given an angle, we can consider an orientation of this angle about this axis. And we consider, again, the counterclockwise convention, because we are using the right-handed rule. So we consider a positive rotation around the axis, a counterclockwise rotation. And with 4 parameters, we are able to define the orientation of a frame with respect to the initial one. And we need 4 parameters, 3 for the axis and 1 for the angle. So still is not a non-minimal representation that would need just 3 parameters, we said, are enough to represent orientation. And in addition to this, so we can use a formula that is called Rodriguez formula to compute the direct problem. The direct problem is getting from this representation, that is the angle axis representation, the correspondent rotation matrix. And the Rodriguez formula is the following. So we have an axis and angle, and we have this. Did you ever seen this? This is called Euler product. Is a matrix, and is very similar to the norm, the square norm. Remember, but is the two the transpose is in the other place. Then we have identity minus this again, outer product, cos delta theta plus you remember the skew symmetric matrix associated to a vector. So this is the skew symmetric matrix associated to the cross product of the axis, sine of delta theta. So this is an outer product, we said. And an important point is that this mapping between angle axis and rotation is not injective. Do you remember what the injective function is? Means that for if you have the domain, we have more points on the domains that correspond to the same point in the codomain. So we have two sets of angle axis tuples that correspond to the same rotation matrix, and we will see afterwards how and why. The opposite, the inverse problem, will give you two solutions. So this means that we have something that is not really minimal here, and this is an example. We will see. We can do with MATLAB afterwards. I connect my laptop and we can do this exercise together, where we start from the an axis 0, 0, 1 with some delta theta, and if you apply this Rodriguez formula, for example, we can see that we boil down to have what? Something that we know, which is the elementary rotation about Z. So we see that in this generic case of Rodriguez formula, for any kind of rotation, if we choose as axis the Z axis, we see that the Rodriguez formula spits out the known matrix of elementary rotation about the Z axis. And this is just for us to ensure that everything works properly. Again, I stress, if delta theta is positive, the rotation is counterclockwise, and if it is negative, is clockwise. So if you, for example, you want to define the orientation of this with respect to this frame, you have a delta theta of 30 degrees and is positive. While if you define the other way, still is delta theta, is not minus delta theta, but the value that is associated to that will be a negative value. And this clockwise thing is strictly linked to the fact that we are choosing proper rotation. So rotation matrix that have a determinant equal to +1. If you use a determinant equal to -1, you will have the opposite one. But we are not masochists, so most of the community use proper rotations, and we will do the same. Then there are some interesting properties of this Rodriguez formula, this rotation matrix computed this way. That is, for example, the fact that if you look, apply the rotation matrix to a generic vector, we saw the last lecture that this vector is rotated. Unless what? Unless you apply the rotation to a vector that is aligned with the axis. In this case, the axis doesn't change, an axis or a scale version of it. And this means that it is invariant. Everything moves but the axis. So this this formula here, what remembers you that you already seen? Saying that a matrix times a vector is equal to the vector itself. What does it mean? Do you remember from? Sorry?
A is the identity matrix?
No, no. It's it's more than that. It's more than that. A is not identity matrix. I can put this. Maybe it tells you something. Yeah. Yeah, exactly. So X, if satisfy this relationship, is an eigenvector of A. And A is not necessarily an identity matrix. It holds also for non-identity matrix, not trivial solutions. And so in the case of a rotation matrix like this, the axis is an eigenvector of R, and is associated to what? What is the eigenvalue is associated this eigenvector? 1, exactly. So there is only one eigenvalue that is 1. We don't know the others. We could be, for sure we have 3 eigenvalues because we have a 3 times 3 matrix. All of them could be real. If one of them is real and the other 2 are complex conjugate, we could have different values. And we will see that we don't see that, but it's just remember that one is the real eigenvalue and the other 2 are complex conjugate. Another property is that all matrix satisfy is that the determinant of the matrix is equal to the product of the eigenvalues. So we know, we see here that since the determinant is 1, the product of the eigenvalues is 1. And also the trace of the matrix in general is the sum of the eigenvalues. And in case of rotation matrix, if you we will see in MATLAB, if you do the compute the Rodriguez formula, you will see that the trace, so the sum of the eigenvalues that correspond to the trace, that is the sum of the elements of the matrix in the diagonal, is equal to 1 plus cosine theta or delta theta. Don't pay attention if I forget to put the delta because they are the same. It's just a notation. And the other property is that R is not an injective map because we have the 2 solutions related to the same, associated to the same rotations. So in the case, if you have a set with an axis R and an angle theta, also the minus axis minus R minus theta will correspond to the same rotation matrix. Then the inverse problem, how do we compute the inverse problem? We start from, we have a big set of rotation matrix, and we want to find the corresponding angle axis, and we call this as the inverse problem. Again, I write a Rodriguez formula, and we see here that for each entry of the rotation matrix, we can write an equation in how many unknowns? 4, because we have theta and we have the 3 component of the axis. And in general, we don't know how to solve this problem, but if we are talking about a rotation matrix, exists an analytic solutions. And how do we compute that? First, we remember what we just said, that the trace of a matrix is equal to 1 plus 2 cosine of theta. And therefore, we can compute theta or delta theta. Sometimes I make confusion between them, but they are the same thing. Is equal to what? I compute the trace, which is, sorry, this is capital R. Yeah. I compute the trace, which is first element of the diagonal, second element of the diagonal, plus third element of the diagonal, and I subtract -1. I divide by 2 and I get cos theta. And then I do the arc cosine. What is the problem of computing the arc cosine? That the arc cosine provides only values in 0 pi. So we won't get the other solution, let's say, that we need. And for we will see later how to deal with that. Not use the arc cosine, but use the arc-tan function. But first, let's find a way to compute the axis coordinates. And you remember that we can write a skew symmetric matrix by subtracting to a matrix its transpose. And if we do that, we see that we have zeros on the diagonal. And if we do that, you do that symbolically in MATLAB, for example, we will see afterwards, you find out that you get this, you get the this expression. So actually you can work out the component of your axis computing this this and extracting from the skew symmetric matrix, that is this one. So for example, we can get our axis, our x, our y, our z. We need to divide by 2 sine delta theta, what? And we said this term is this one and is the z component with opposed sign. So we take the R21 minus R12. Then we have the y component here, that is this one, that is as is. So R13 minus R31. And then we have the x component with opposite sign, that is this one. So we change the sign, R32 minus R23. Okay, cool. Now we have we know how to compute the theta. Not really satisfied about that, but we have at least a method, and we also are able to compute the axis. What is the problem in this situation with this formula?
That the sine of theta would be 0.
Yeah, so we can have a division by 0 here whenever sine of theta is 0. So we have two angles that create problem that are, for example, delta theta equal to 0 and delta theta equal to plus minus pi. That are two angles for which sine of theta is 0. And these are called singular cases. For these cases, the axis is not defined. Okay. But we said that we are not satisfied with the arc-cosine because the arc-cosine, in general, we don't like either the arctangent or the arc-cosine. Instead of using them, we want to use the A2 functions. And the A2 functions is always defined in the 4 quadrants. So if you think about the angles with 0 angle here and 90 degrees here, pi here, minus 90 degrees here, this is the first quadrant, and this is the second quadrant, third and fourth. So, for example, if you use the arctangent, you can use the sign of the input argument to define what is the quadrant, because you know the A2 is, let's say, when you compute the arctangent, you do the y component divide the x component, which is the sine divide the cosine. But and then you do the arctangent. In the A2, you have the sine here and the cosine here. So in the case of the A2, you are able to, while the arctangent provides you only output between minus pi half and pi half, minus 90 degrees and plus 90 degrees, the A2 provides you for all the angles but the origin. But this case never happens because you never have both cosine and sine equal to 0. So using this and knowing that the norm of the axis is 1, again, doing this subtraction and knowing that the norm of R is 1, we know that the skew symmetric matrix associated to the cross product with this vector V will, if we compute the norm of V, we have something like this. So we, knowing that the norm of this is 1, we can compute simply the norm of this vector V and divide by 2 if we want to compute the sine of delta theta. Since we do the square root, we have 2 solutions. And then to compute delta theta, instead of using the arc-cosine, this time we can use the A2. So instead of using, so ideally we instead of using the arc-cosine, we could do arc-tan of sine delta theta or cosine delta theta, but we don't want even to use the arctan, so we use the A2 function, which is we replace sine delta theta, so we divide plus minus 1/2 of RP2 R23 R13 minus R31 squared plus R21 minus R12 squared. And a second argument, the cosine that we found before, that was the trace minus 1 divided by 2. Okay. And we use this expression if we want to compute the solution. And we see that since we have a square root here with 2 plus and minus solution, we get the 2 solution we were expecting, that tell us that this mapping is not injective and that we have two solutions. While if we want to, now we want to see, okay, then so as an exercise, you can check the computation of a singular case. And a singular case we saw that is resulting in a sign of delta theta equal to 0. We will see this in MATLAB. And yeah, something is missing. The summary. Okay. A side note is that the angle axis representation can be equivalent to a rotation or Euler vector, which is if you multiply your delta theta times the unit axis, you get this vector. And we will see that we will use this in the exponential map. It is an equivalent way of representing orientation that is minimum, is a minimal representation of orientation. And you will use this with Andrea Del Prete in the next course next year. And for example, if you have an axis angle like this, 90 degrees angle about z-axis, this is the associated Euler vector. Okay. Then another formula that you can use, rather than using the Rodriguez formula directly, you if you want to rotate just a vector, you could simplify the Rodriguez formula and obtain a single formula without having to first multiply the rotation matrix and then multiply for the vector to rotate. So this is a rotated vector. This is the matrix that you remember rotates the vector. This is the original vector. If you replace the Rodriguez formula here to compute the rotation matrix associated, and you have the vector here, you can simplify this way, and you end up with something like this formula. 1 minus cosine theta, and you can rewrite. This is scalar. You remember, is a scalar product, so you can put either on the left, for example. There's no problem. To be more clean, and then sorry, you multiply by r hat, which is the unit vector, and then we do this. Okay, this is just a side note if you want to be more efficient in your code. In a summary, now we see why these angle axes are also are useful. We can, when you want to plan orientations, we can do the interpolation on the delta theta axis. So now we are, it's licit to do this. We start from the initial angle and we subtract from the final the initial one, and we have the scalar S that is the time parameterization that goes between 0 and 1. So this is very useful to do interpolation. Still is not minimal representation because we have 4 parameters and the components of R are constrained by the condition of having unit norm, because we said unit axis. Unit norm. And also, we said that the mapping to rotation matrix is not unique. Okay. Then we can introduce the exponential map. It is something very similar and equivalent to the angle axis representation. And the idea is that given an angular velocity vector applied for a unit time, we want to compute the equivalent rotation matrix of this rotation, of the rotation with that angular velocity. And for example, consider a trajectory on the rotation, time varying rotation matrix. And we want to use the properties that we saw, that is linking the time derivative to the angular velocity times vector product, the rotation matrix itself. That could be rewritten as I said, the associated skew-symmetric matrix to the cross product of omega times r. And if you look closely to this system, to this equation, it's a differential equation of a dynamic system first order that you know that as a solution with exponential starting from the initial value x0. So in an equivalent way, we can integrate this differential equation with the rotation matrix, where this is equivalent to the A matrix. And to do so, we use the exponential, but this time is not an exponential of scalars, but it's an exponential matrix. And this is the initial orientation. So this is we use exponential of a matrix here. In MATLAB, where in MATLAB is represented by the function exp_m. And if we set the initial orientation as identity for a unit time, we have what people call the exponential map. So it's if you do exp_m of a vector omega, you get really a rotation matrix. So you get a matrix that satisfies the properties of orthonormality. So belongs to the group SO3. And in this case, if we consider this as this angular velocity that you don't know, you know that has no, not necessarily a unit norm, but could have whatever magnitude. And we split in its unit norm part and a scalar that represents its magnitude. We see that we will go back to the previous Rodriguez formula that we said before. So if we get this expression, we don't know how to deal with an exponential of a matrix, but we can do a Taylor expansion of the exponential. So as the same as an exponential, a scalar exponential, we can do a Taylor expansion of that, and this has this relationship where you have the linear term, you have the quadratic term, and the cubic, and so on. But it can be proved. I don't do it here, but that this Taylor expansion with the specific properties of the skew-symmetric matrix can be transformed into something like this. So something that is related to omega skew symmetrics and omega squared skew symmetric. And you can recognize from here that this is the Taylor expansion of sine theta and of 1 minus cosine theta. And you can find more resources in this paper on this development. And the cool thing that we want to show is just that if we write this down, we will see that we can get the Rodriguez formula from this. This is a variation of Rodriguez formula and that you can apply, will give you the same result. If you compute the skew symmetric matrix squared as this expression, if you don't believe, you can do it symbolically. And we see that if we replace this omega hat with r with our axis, sorry, a hat is missing, and we consider a property that you remember, if you do the square of a skew symmetric matrix, this is the outer product minus the norm times the identity matrix. But because the norm of a unit vector is 1, then this boils down to just be I. And if we replace, sorry, I'm filling up partially the slides to I plus sin theta. So we look at this. Plus this 1 minus cosine theta, and we replace this. This is again I plus sin theta this plus minus r transpose cosine theta minus I plus I cosine theta. We see this simplifies, and we go back to the Rodriguez formula, which is I minus r transpose cosine theta plus sin theta. Okay. Yeah, and this is the Rodriguez formula. So we see the exponential map, it's equivalent to angle axis. So to summarize, the exponential map is mapping a vector, an Euclidean vector, represent an angular velocity, but that is the axis times this theta angle into a rotation matrix that belongs to the group SO3 as this expression. So you both this and this are equivalent. They provide you a rotation matrix that satisfies the orthonormality properties. And given, so the idea that given omega, the exponential map computes the rotation matrix that you will obtain applying that omega for a time unit, so for 1. And the inverse of an exponential map is called the logarithmic map. And you can use in MATLAB the function log m. And this does the opposite. So from a rotation matrix, brings down the angular velocity. And you can compute using this function in MATLAB and it provides you what? Provides you if you do the logarithm of the rotation matrix, you get the argument of exponential. That is a skew symmetric matrix. So then you can take out the value of the omega vector and compute the axis and the theta. Equivalently, you can do whatever we saw before from the trace, and from the skew symmetric part you can compute the axis and the angle. So this is equivalent to what we saw to the inverse problem of in the angle axis case. So as a summary, exponential map is a minimal representation because we three-dimensional map without constraints. We still have singularities in 0 and pi, and also it's not injective. If we, for example, compute the exponential map with an angle theta, or we sum up 2 pi, 4 pi to this angle theta, you obtain the same rotation matrix. So yeah, now I will show you some exercises with this. We can if I MATLAB. Do you have any question about this? Everything is clear? I put these exercises in MATLAB on the server, on the folder of the slides. Sometimes I update them, so I try to change the okay. Yeah, you can do the take a break now. I will set this up so you don't waste time. Let's say a 10 minutes break. Okay. Okay. That should be okay. So let's see now some exercises on what we just said. If you look at the rotation matrix.m matter file, first we define some. Sorry, you cannot see this. Duplicate. First, we define some anonymous function at the beginning that we will use a lambda. They're also called lambda functions. So you consider like the argument as input. In this case, we want to compute the skew-symmetric matrix associated to the cross product of a vector v, and we also define the free elementary rotation matrix about x, y, and z axis. So first, let's solve the direct problem. So we want to get the rotation matrix from a certain angle axis set. We define an axis like this way. That should be a unit axis. You can compute the norm of that. And the angle, we can put, I don't know, 0.3 rad. And we apply the Rodriguez formula, that is the following we saw before. We get R. And now we can check just that R has determinant equal to 1 and is orthonormal. So we can check that R inverse is equal to R transpose. Yes. So this is just a very small number. It's just a matrix of zeros. Instead, if we want to compute the Rodriguez formula symbolically, as we to see that the relations that we found are correct, we define some variables as symbolic, like axis, components, coordinates, and the angle. We should append a value, a label real, just to don't have complex solutions and weird solutions. So we define a vector of symbolic values called axis. We apply again the Rodriguez formula. This time we get a big expression. And if we look at the trace of this, it has the expression that we saw. We can find that if you compute the trace, we can find that is 1, that is the norm of the three components of R is 1, plus 1, 1 plus 2 cosine of the angle. And instead, if you compute the skew-symmetric difference between R and its transpose, we see here that we get minus 2 RZ sine of angle, so the expression of before. And if we divide by 2 sine of angle, we get the again the skew-symmetric of the axis. So for the inverse problem, so we get the direct problem. We compute the rotation matrix numerically. We saw that this stuff works symbolically, and we want to verify that the inverse problem will provide our axis and our angle back. So the angle, this time we apply just the cosine, but you can apply also the arctan 2 formula, and you see that you evaluating the arc cosine of trace -1 divided by 0.5, so by 2, sorry, divided by 2, multiplying by 0.5 and do the arc cosine, you get the angle. Somebody of you found an error, a typo in the slides. I will correct it. I was dividing from 2 by 2 out of the arc cosine, so that was wrong. For the axis, we do the following. We apply just the formula we saw, and we see that the axis is the same as the starting one, which you compute the direct problem. Now the singularity. This was the example of a singular case that I was showing you in the slides. So we can evaluate the rotation matrix associated to these time terms, and we want to check is a rotation matrix. So we first consider that the norm of each column, sorry, this is a 2, should be 1, and we do an AND. So if this is 1, it means that all the norms, all the columns have norm equal to 1. Orthogonality, so we do the dot product of the columns. Again, we do an AND. We see that they are orthogonal, and also the determinant equal to 1. So this is just a simple test you can always use to check if a rotation matrix is a rotation matrix. 3 times 3 matrix is a rotation matrix. Then again, we want to apply the inverse formula. We get an angle of pi, and here we start to have problems of sine of theta equal to 0. So for some reason, MATLAB, when you compute the axis, you get something that explodes, no longer a unit axis. The second exercise was to rotate a vector. So this is the original vector we want to rotate, and we want to apply rotation that is angle axis representation, let's say around Z of 0.2. So angle 2, and we apply just the formula that we saw previously. We get this expression for the rotated vector, and we want to see that the result is the same as we apply the elementary rotation around Z. That is the formula that we saw, we define above with the anonymous functions applied to the vector B. So this is evaluation. We see that the two vectors are the same. Then the next exercise is on the exponential map. Again, we take the angle, this axis and this angle, and we want to see basically that the three formulas they provide is the same result. So this is the formula, Rodriguez formula. And this is the formula with the exponential map, applying the function exp of MATLAB directly to the cross M of Rotvec, where Rotvec is the product, is what we call the angular velocity without hat. So it's the product of the axis and the angle. And we want to see that it's equivalent to the Rodriguez formula variant. Apply this, compute R this way, get this R, we compute this way, we get the same R, and in the third way, again, they are the same. Then we want to show that the non-injectivity of exponential map. So we compute exponential map for the angle, and also for the an angle plus 2 pi, and we see that they are the same, because if you subtract one from each other, you get zeros. Very small number here that is basically a matrix of zeros. The logarithmic map, it's a log m function, and we wanna see that we get the skew symmetric matrix associated to this, that is this one. And if we take the element, this will be the z component of rotation vector. This will be the y component and the x component, I think. And if you compare with the rotation vector that we defined before, the values are the same, just column and row. So again, we show that you can get from the inverse problem back to the original input that we used for the direct problem. And then I think we can move to the next topic, that are the Euler angles. So I change back to my surface.
We cannot hear you.
Sorry, thank you. So what are Euler angles? Euler angles are a minimal representation of orientation. Think about Euler angles as a set of subsequent orientation, and this orientation should be about independent axis. So the set of Euler angles is like understand why it changes color, is a set of free angles that you use to represent the orientation of a frame. And this set of angles is not a vector, just a sequence of angles. Why? Because it is not part of a vector space, so it can be combined two set of angles, you cannot sum them up and obtain another angle, another set of angles. As I said, the Euler angles are a sequence of rotation around the independent axis of reference frame. So think about independent axis. If I do a rotation about a z axis, and then I do another rotation again about the same z-axis, these two rotations are not independent axis rotations. So they should be about different axes. And this axis could be of two types. They could be fixed axis or moving axis. So if you think of fixed axis, you always think about rotation about the original frame, inertial frame fixed on the lab, let's say. And the moving axis, it means that you first rotate about one axis, then about the subsequent axis, then about the other axis again. So every time you change the reference frame. And there are 12 possible combinations of moving axis and 12 fixed axis. And as you said, they cannot be contiguous axes, so no xxz or yzz. And these are all the possible combinations. So for example, a rotation about the x-axis, then a rotation about y-axis, then again about the x-axis, or all the other combination, x, y, and z. And all the combinations are for the, in this case, fixed axis. And if you do a rotation about x, let's say an axis x about another axis, and then again about that axis, we call these angles proper angles. Otherwise, if they are done about axes with different names, they are called tight Bryan angles or Cardan angles. And we said that the same is for moving axis. We will discriminate the moving axis with a prime or with a second, with a superscript here to discriminate them from the fixed axis. And we will see that only 12 combination matters, because we will show that doing a rotation, free rotations about the fixed axis is equivalent to do the same rotations about a set of axes that are opposite, and we will see that later. So in essence, there is an equivalence between the two. We will consider only moving axes in this course. So because they are more intuitive, while in the fixed axis, you do the rotation always about the initial frame, and you need to remember how was that located. And as a sequence, we say we have 12 sequence. For the moving axis, we choose this one. We choose this one, which is mostly used in robotics, and is the one that does a rotation first about z axis, and we call this angle phi. To be consistent with the book of Siciliano, then a rotation about y-axis. This is, you see, this the initial one. We do a rotation about the z-axis, and the z-axis will be the same as the fixed axis, because that's why we don't put any superscript here, because they will be coincident at the beginning. Then once we did the rotation, the first rotation, we see that the new axis, new x-axis, will be rotated, and we do a rotation this time about the y-axis, and you will see that again we will have these two axes changed, and then we will do a rotation about that axis again and find another frame. And these are called theta is phi is called roll, theta is called pitch, and phi is called yaw, theta is called pitch, and psi is called roll around the x-axis. The problem of this moving axis is that this axis won't be orthogonal because the axis location depend on how much rotation did you do with the about the previous one. And so if you want to, for example, see this axis in our robot, quadruped robot, you see that the roll is about the axis coming out from the face of the robot, and the lateral one is the y-axis, and the vertical one is the z-axis. And these are called roll pitch yaw. Then the direct problem, we said we want to, direct problem is when we want to compute the rotation matrix associated to this set of Euler angles. So because this set of Euler angles phi capital, the expression of a rotation matrix is equal to Rz phi Ry theta Rx C. And you remember these are, we saw them, they are elementary rotations. That's why Euler angles are convenient, because you will see very convenient to want to find an orientation. You apply free elementary rotation and you use the anonymous function that we saw in MATLAB. And these are subsequent rotation, one about the z-axis, one about the rotated y-axis, and the other one about the rotated again x-axis. And these are moving axes. And you see that this is the order of rotations. Successive rotation means post multiply the previous rotation with the following one. And these are the elementary rotations. I recall the expression of the elementary rotation that we already saw in the previous lecture. One about the x-axis, we see that one is here, the other one about y-axis, the one is here, and the other one about x-axis, the one is here. Everything's clear? If you multiply this multiplication subsequent rotation, you find this expression. And remember, this expression only works for this set of Euler angles that we choose among the 12. Okay, so z, y, x, about moving axis. Because people, whenever need to use Euler angles, need to always define what is the sequence they are talking about. Otherwise, there is no meaning, there is no common ground to discuss. And we will see this, we obtain in MATLAB, we will do an exercise to obtain this matrix. And the issue of not having non-orthogonal axis is that we cannot compute, for example, the orientation error as we saw, subtracting desired values from actual values. Actual values from desired values. So this is not true. The orientation error cannot be defined like this, because the orientation error should live in an Euclidean space, so in an Euclidean space with the orthogonal axis. And therefore, when we want to do tracking of orientation with Euler angles, we need to map them to other representation like the angle axis. or rotation matrix and use a different or quaternions. We will see the last one is quaternion. If we want to do the direct problem with fixed axis, not with the moving axis, as I said, we can get the same rotation matrix if we shift the order of the axis. So rather than doing first Z, then Y, then X about moving axis, we do rotate first about X, then about Y, and then about Z. But these rotations are not elementary matrix. So they have a more complex definition, and they are not as, that's why we never work with fixed axis. We use moving axis because these are much simpler to compute and more intuitive also to think about, because you want to think about, I need to define the orientation on my wall, an inclined wall, to go with my robot, a ramp, and I think about rolling pitch or rolling pitch inclination. Is much easier than thinking about fixed axis. But just remember that there is an equivalence between the two, just shifting the order. So these two will give the same results. This is about the moving axis, that is about the fixed axis. Then the inverse problem, we said the inverse problem is to go back from the rotation matrix to the representation. So to get a clue on how to do that, we can have a look to the face of the rotation matrix. And if we inspect that, what we can see? What we can get from intuition here on computing the values of phi, theta, and psi angles. First, we can see that here there is only theta. Here have the cosine of theta, sine of theta, again cosine of theta. Here we have cosine of phi and sine of phi. So, for example, we can try to get phi dividing the sine, this term, by this one. The cosine will eliminate, and we get the tangent of phi. But we say we don't like to use the tangent, so we better to use the a tan 2. So we can do a tan 2 of these two inputs, but we need to pay attention that R21 and R11 they contain this term that can go to 0 and make us our a tan 2 not defined. Then for theta, we can consider sine of theta here minus R31, and as a cosine of theta, we can square these two terms, and we will see that we get, if we square them, and we sum them, and we collect cosine of theta, we see that this is from the trigonometry property, it's 1. So we get cosine of theta squared. We do take a square root, but here we see the problem with Euler angles. We still have two solutions because of a square root. So we always have a pair of solution. And for the third one, the phi, we get, we consider only these two terms. We do the atan2 of this, this one, and divide by cos theta. And again, we see here that whenever cos theta becomes 0, we have issues. So this is at 0. What does it mean having cos theta equal to 0? It means that we are in singularities. So the solutions degenerate whenever cos theta is equal to 0. And cos theta is equal to 0 means, for example, when two axes align. And this is called the gimbal lock problem. And happens in the case of this sequence that we choose for theta equal to plus minus 90 degrees. So whenever you have a pitch of 90 degrees, you cannot recognize, you cannot solve the inverse problem. What happens in specific? We replace in the previous expression theta equal to, for example, 90 degrees, and we get this formula. And if you look at that, we see that from the information in this matrix, we can only retrieve information about the sum or the difference of phi and psi. Because if we apply the trigonometric formula of sum and addition identities that we saw, we can see that this one is equal to sine of psi minus phi. This one is equal to cosine of psi minus phi. This is the same. And this is the minus sine of psi minus phi. So in here, you know that you can solve for get information on the difference, these two angles, but not on them separately. So you cannot discriminate between yaw and roll anymore. And this is what happens in a singularity situation. And again, if you use a different sequence, you will have a different point set of angles for which you have singularities. So if you look at the drawing, this is whatever happens in a normal configuration with all pitch yaw not aligned, while in the singularity you get the yaw axis aligned with the x-axis, so you don't know, you can either move phi and psi, and you won't have any you don't recognize the effect is due to their sum or difference, depending if you are using minus pi half or plus pi half as pitch. So you cannot distinguish between psi and phi, and this means that to the same rotation matrix we have an infinite set of angles that correspond to the same rotation matrix. For example, if in this case, if you compute the rotation matrix of these angles, roll, pitch, and yaw, and you compute this one, sorry, this one, don't think about it, was wrong, you get the same result. So in this case of a singularity, the chosen representation of Euler angles is not able to capture the orientation associated to the rotation matrix. And you can repeat this analysis for any sequence of the 12 that we saw, and you will always find two solutions and singularity for some values of the angles that will be different in any case. So knowing the task that you want to do, in our case, we choose this sequence because we know our robot will never go with 90 degrees pitch, because it's very dangerous. It's not a humanoid. So its trunk is always, let's say, shifting between plus and minus 30 degrees. It will never go maximum 45, never go completely vertical. So that's a limitation of Euler angles. And another thing that we need to know is how to compute the angular velocity. That is from the derivative of the Euler angles. The derivative of Euler angles, we call them Euler rates. And the angular velocity is a vector that lives in an Euclidean space, so with orthogonal axis. And we can sum the contribution of each component in any order. We don't care. While in the case of Euler angles, we need to respect the sequence. So to map Euler rates into omega, we start from the orientation we have, and we want to see how, for that orientation, the derivative of the Euler rates will map into an angular velocity, because we need orientation, but we need also, for example, if you want to do control of orientation, we need the damping term, and the damping term will depend on the angular velocity. So we need to work also at the velocity level. And so as input, we have the orientation we have at that moment, and the set of Euler rates that we want to map. They don't belong to a vector space, and again, a sequence of two rotation is not obtained summing the corresponding minimal representations. You cannot sum these angles. And in general, as I said, the angular velocity is not equal to the Euler rates. This means that, for example, omega is not an exact differential. If you do the integral of omega, you don't get the orientation, the set of Euler angles. While if you do the integral of the Euler rate, you get this the set of Euler angles, a set of Euler angles relative to that integration. So integral of omega doesn't have any physical interpretation. Let's consider two sets of rotations. First, we rotate, for example, for 1 second about the z-axis, and then for another second about the x-axis. And we see that if with omega equal to 1, I think, and we see that omega equal to 90 degrees per second, and we get this. If you do the integral, we get this number. And we know that if we rotate first about z and then about x, we get this orientation. While if we do the opposite, that is, we first rotate about x and then about z, we get this orientation that is different from this. But if we integrate omega, we get the same value. So there is a mismatch in this sense. So that if it was an exact differential, it would provide different value of orientations, not the same one. And while for linear velocity, we know that the velocity is the time derivative of position. So for orientation, omega is not the time derivative of the Euler angle that represents orientation, even if they are 3D vectors. So if somebody in the community is tempted to do that, that is wrong. And this why, because this is why considering translation doesn't matter in which order you translate. You can translate first about y and then about x, or first about x and then about y, and you will end up in the same point. While for orientation this doesn't work, and the order matters. And if you rotate about one axis and then about the other one, you don't get the same result that do in the opposite order. Okay. So how do we? It's still possible to find though the relationship between the omega and Euler rates for a certain orientation. Let's consider the same sequence that we introduced before and compute the contribution of each Euler, a component of a Euler rate vector to the omega. So omega is defined in Euclidean space, so it's a fixed frame. And the first rotation we said is about the z-axis. So we put the z-axis here and we multiply by the Euler rate phi dot. And this is the contribution due to the first to the phi dot component of the Euler rate. Then we do a rotation about the we did this rotation, so we saw that the y-axis, the x-axis, sorry, has moved, and the y-axis as well has moved from the original ones. And now we want to rotate about the y prime axis. That will be this one. So because it has like a sign, minus sign of phi, and on the x component, and cosine of phi in the y component, and we apply this component of the Euler rate. And the third one is the rotation about the x second axis, and therefore is like again rotating, computing the applying this rotation to a vector that is rotated 2 times. So the x second is due to the rotation from the x to the x prime, and then again rotating again from the x prime to the x second. And if we put all of this in matrix form, we see this is the z-axis. This is the corresponds to the second column of the elementary rotation matrix. That is representing the y-axis. So it's a rotated axis. And this is the first column, so the x-axis of the composition of the rotation about z and about y. And this matrix here is dependent on only phi and theta. So it's dependent only on the angles about x-axis and theta axis and y-axis, sorry, about z-axis and y-axis. And we can sum this contribution in a matrix way and find the omega. And this mapping, as I said, depends on the actual orientation. So you will have a different mapping for each orientation. It's a non-linear one. So this matrix will be different for each orientation. And if we do the determinant of this matrix, we get cosine theta. And this means that for theta equal to plus minus 90 degrees, we have a determinant goes to 0. And this means that we are not able to define the mapping between Euler rates and omega. And this is called a singularity for this Euler rates to omega representation, because t cannot be inverted for this situation, where cosine theta is 0, which means again for the same singular situation as in the previous mapping that we saw. So also at the velocity level we have this singularity. So it doesn't exist, and there exist angular velocities that cannot be represented with this a set of Euler rates. So you have problem in this configuration. And again, for different sequences, you have different very different expression for the matrix T, and different values of singularities. To summarize, Euler angles are minimal representation of orientation because they have only 3 parameters. They have singularity, and this is the price to pay for a minimal representation. Usually you do have this. We will see that in quaternions you don't have singularities, but you have a non-minimal representation. The other problem is that they have not orthogonal axes due to the fact we are using subsequent rotations. And the advantage is that they can be easily numerically integrated. So you can plan a trajectory with Euler angles. You say I want to move from this orientation to moving just the z component, and you can easily do that with Euler angles. Everything is clear? Let's say in our code, we always start using linear angles, knowing that there are this singularity problem. But then if you want to do, for example, somersault or jumps that you do a full rotation of the body, then you need to use another representation that we see people usually do use quaternions. Indeed, the quaternions are called unit quaternions. They are 4 parameters. They are a non-minimal representation, but they have no singularity. And the shortcoming is that they have a unit norm constraint. Think about a quaternion in this way to get an idea. You can think about how do you represent a point on a circle. In polar coordinates, you can use a parameter that represents the ray distance from the origin and the angle with respect to an axis, to a 0 reference. In 3D, to represent a point, you can do the same reasoning and use again the ray, the radius, and 2 angles. Okay. Now, if you do this for a 4-dimensional sphere, you get a quaternion. So you get a scalar that represents a radius of 4-dimensional sphere and 3 angles. Sorry. I have some delays. Okay. And these quaternions are useful because they eliminate the problem of singularity that we find in angular axis representation. And therefore, for example, they are used, for example, to describe satellite orientation or space applications where you cannot have these issues. A quaternion is composed from a scalar part, we said, and a vector part, let's say the 3 angles in the 4D sphere. And the scalar part is in R, belonging to R, and this one to R cube. They suffer from this problem of having need to have a unit norm. So you do the squared of the scalar part and of the vector part, and it should be equal to 1. You remember this is the norm for a vector, and the nice another nice property is that they don't have the problem of having 2 solutions for the same orientation. So for the for example, what we had in the angle axis representation will give, this will correspond to the same quaternion and to the same rotation matrix. We don't no longer have the duplication. But to do computation with quaternions, we need a special algebra. And what we need for in an algebra to do computation at minimum, we need to represent the fact we don't do any rotation, and we represent this with this kind of quaternion that has a 1 in the scalar and a vector of zeros in the vector part, and this corresponds to, for example, to the identity in the rotation matrix. So the is the neutral element. Then we need the inverse of define the inverse of the quaternion as we did for rotation matrix, and this will just flipping the sign of the we've done just flipping the sign of the vectorial part. And we also need to compose rotations, define a quaternion multiplication. So let's say a quaternion, we want to define the orientation that is resulting from the composition of two rotations, and one represented by the quaternion Q1 and one by the quaternion Q2. And in this case, this is the formula. So you for the scalar part, you do the following, and this is for the vectorial part. This is just you will call this function whenever you want to compose rotation through quaternions, and is represented by this quaternion multiplication. We have possibility to map and convert quaternion and angle axis. So this is the angle axis to quaternion. So whatever we saw before can be easily mapped into quaternions, and this is the whenever you have small angles, the quaternion correspondent boils down to this very simplified formula. And then from quaternion, you can compute also the angle axis in this way. And you can see that the axis is just the vectorial part divided by the norm of the vectorial part. And since the norm is one of the quaternion, then you can compute the norm of the vectorial parts doing square root of 1 minus the scalar part squared, because remember I cannot write anymore. Yeah, I think PowerPoint has some issues. Okay, it's getting very slow. Then we have also the Rodriguez formula to map quaternions into rotation matrix. Again, we have a skew symmetric matrix associated to the vectorial part epsilon. And you can find in this document a lot of information on Euler angles, quaternions, and so on. Seems that Zoom crashed. Okay, Octavio, can you hear me?
Yes, we can still hear you and see you.
Okay, that's crazy because I arrived a message that everything crashed here, but you still can see me. Okay, and now we can do some MATLAB examples on the computation of quantities that we just defined. And I will go to the other computer. Okay, can you see the MATLAB screen?
Yes, we can see the MATLAB screen. Talking, Dr. We still cannot hear you. Professor, we cannot hear you.
Sorry, guys. I had to switch from computers and I need to mute and unmute the microphone, and I forgot this this one closed. Now, can you hear me?
Yes, yes, we can hear you now.
No, I'm sharing this. Cosa? Ah, sì, no, che siccome non di solito dico di farmi le domande, ma sto giro non potevo sentire. No, perché ho tolto anche il volume. Sì. It's very complex to manage all this. Sorry. Now can you hear me?
Yes, we can hear you.
Okay. Yeah, I'm sorry. I reduced the volume in this laptop. Yeah. So nothing. I was just showing the application of the formula we presented in the lecture, and so demonstrating that we can compute a singular matrix for the value of pitch of minus 90 and plus 90 degrees, and showing that both of them they give the same solution. So here is the symbolic expression that we analyzed, and putting the numbers inside, you get the same rotation matrix. And in this exercise, we were just applying the formula for the direct problem, which is applying subsequent rotations, elementary rotations about the z, y, and x axis, and then getting back after computing the rotation matrix, the angles, the original angles, applying the inverse problem formulas. Then for the mapping between Euler rate and angular velocity, we apply the formula that is in the slide, and this is exactly what we have here, because phi, that is yaw, the angle for the yaw, and I should be consistent, sorry, 0.01 for this axis, and minus sine phi cos phi. And if we evaluate this, we multiply for the vector of Euler rate that we, vector of Euler rate we want to compute the omega from, we get the value of omega in the inertial frame, in the fixed frame. And we want to check that this mapping has some singularity in correspondence of 90 degrees as well, or minus 90 degrees. And to do so, we check, we have this anonymous function, we call it with, for example, whatever number for the roll in yaw, and applying a 90 degrees for the pitch. And if we do so, we get this matrix. And if you compute the determinants, we see that it's going to 0. So singularity in this case has a determinant equal to 0, and means that we cannot map Euler rates into omega. Okay, we can do another very short break of 5 minutes, and we'll go back to the next slide in the other computer. Okay. Sweet. Okay. I understand why you have this. Okay. So this, now we start the get into the core of the kinematics. We discuss about the different kind of orientation representation. Now we want to put everything together with also the description of translations and define the kinematics of a rigid body initially, and then putting them together, the rigid body that represent the links of a robot and having the direct kinematics of a robot. First, about kinematics. Do you know what is the definition of kinematics, in your opinion?
The motion without forces.
Yeah, correct. So kinematics cares only about the description of emotion without considering the forces that cause the motion, because the study of the influence of the forces is the matter, the subject of the dynamics. With kinematics, we just care about description of emotion. And so we know that by moving its joints, the robot changes the position and orientation of the end effector, but not only of the end effector, also of all the other points in the structure of the robot. So in studying the direct kinematics of the robot, we are able to compute the position and orientation of each frame that could be attached in any point of the robot as a function of what? Of the joint variables that we represent in this case with a Q vector. So in the kinematics, we have different spaces. To have a motion of the joints, we need to actuate the actuators. We saw that we have a relationship with jointed actuators. And usually this relationship is one-to-one. We can see an example where it is not. And so we have actuation space, the joint space, and the task space. The joint space and the actuation space can have different dimensions. For example, in this case, whenever you use two motors that work in an antagonistic way, but both of them will actuate on the joint variable. So think about this is one joint. So we have two motors to move one joint. But in this course, we don't consider this. we assume one motor per joint. So the dimension of the joint space is the same as the dimension of the actuation space. And we completely neglect the actuation space for now. To describe the joint space, we use what we call generalized coordinates. So suppose we have, for example, a system of n rigid bodies moving in the space, free to move. How many degrees of freedom do they have? The total number of degrees of freedom of the system. All the let's say n bodies, 9 what in total?
6 times n.
6 times n. Okay. Then let's assume we are going to limit the motion of these bodies, these links floating in space. And we limit this motion in certain joints. And these joints will allow only one relative movement between two bodies. So in this case, we eliminate, of the 6 degrees of freedom of each body, we eliminate 5 of them, because we introduce constraints between any two subsequent links, any two links. And we call these constraints holonomic constraints because depend only on position and not on velocity. We will see later on in the contact dynamics how to define these holonomic constraints, and we will better detail on that. And in essence, we have 5 scalar equations that remove this algebraic equation that remove these degrees of freedom. And we remain with what? We remain with 6 times n minus s, which is 5 times the number of joints. So we remain with n small coordinates that we call generalized coordinates. So we remain with a number of coordinates that is a number of degrees of freedom that is equal to the number of joints. So the generalized coordinates are coordinates that allows us to represent our system while implicitly taking into account the constraints, and represent the number of degrees of freedom of the mechanical system. And the important thing is that the generalized coordinates should be minimal and unambiguous. And they can contain what? They can contain, depending on the nature of the joint, linear quantities or angular quantities. So if you have a rotational joint, we will have a generalized coordinate that is an angle. And if you have a prismatic joint, you will have a generalized coordinate that is it's a position, a linear position, relative of one link to the other. So we have 2 spaces. We said we don't consider the actuation space. The joint space is where we have the actuators acting on, and the actuators are usually placed along the structure, and and then this actuator will move these joints, and usually these joints are, for example, rotational ones, and they're not affecting, they're not directly commanding Cartesian variables. So they, in case of rotational joints, they command an angle, they control an angle, so they live in a space, in a joint space that is not a Cartesian space. And while the task space usually is where we define the our task. It could be even the joint space itself, but it usually is is for example the end effector space. And to go from the joint space to the task space, we said that we use the direct kinematics that maps joint position in the vector position, for example. And the inverse kinematics instead is doing the opposite, is mapping and the vector position or Cartesian position of some whatever point into joint positions. And so the space of the joints is defined by the vector of joint variables we call Q, Q1 and Qn. Q1 is for the first joint and Qn for the last joint. And for this Q, we need to choose a parameterization. And this is a way to describe it, to describe this configuration. And this parameterization is done with generalized coordinates that are minimum and ambiguous. And as we said, is the number of degrees of freedom is equal to the size of this generalized coordinate vector Q, and is equal to the number of joints. We have here two examples, for example, of parameterization choice. We could, if we want to define the joint space for this robot, we could use, for example, either this angle for the first joint and this angle for the second joint, or we could do whatever most people do in robotics. We use for the second joint angular position, we define it in a relative way with respect to the previous one. So this is, both of them are okay. They are minimal. Here we have a 2 degrees of freedom robot with 2 joints. In this case, it's a planar robot. And they're minimal and unambiguous. While in this case, for example, we have 1 degrees of freedom planar robot with 1 joint here that moves these links around. And in this case, is it unambiguous, this kind of parameterization, if we choose, for example, to represent the joint space with these 2 variables, x and y? Well, it is unambiguous. We can represent the configuration of this link with x and y coordinates for each point, for each configuration. Sorry, for each configuration, we will have a different couple of x and y variable. But is it minimal?
No.
No. Why?
You can use the angle.
Yeah, because let's say there is implicitly, if we choose x and y, there is a constraint involved into this. That is that, for example, this point cannot be the length of this segment cannot be bigger than L squared. Sorry, the length squared it should be the x and y component should be related to the length of the link, for example. So we have 2 variables, but they're not minimal because in the end we have 1 degrees of freedom and we need to add a constraint. So ideally we just need 1 variable. So this is a non-minimal representation, and this is not good for set to represent the joint space as generalized coordinate. What about the operational space or the task space? Both names are the same and equivalent. So the task space is the space where the task is defined, and usually where the trajectory are planned. So, for example, if you want to move the vector on a 2D plane, we have a 2D task. If you want to drill a hole perpendicular to a surface, we do have a 1D task. And the important thing is that the direct kinematics is defined for each task. So we first define the task, we have a joint space that is always the same, and we can find this direct kinematic mapping for each task. So the direct kinematics depends on the task. Other example of tasks are to move the position of the end effector, move the position and the orientation of the end effector. So in this case, in the first case, you have a task of 3 dimensions. In the second case, you have a task, 6-dimensional task, but you could also do other things. For example, you have a camera in the end effector, and you want to do visual servoing, visual tracking. So you want that some feature in the image plane of your camera are tracking some desired ones. So you want to follow an object, for example. So you want to, in this case, the task is defining the image plane, image plane of the camera. And still you can find a direct kinematics that relates the motion of your joints to the motion of the feature in your camera plane. So you can be very creative here. You can put together many things. You can put orientation and position. You can do control of position and orientation only in 2 directions and leave the third free, or you can do control the position in 2 directions and give the third one free. So this is just to say that tasks are not limited to the Cartesian space, even though we mostly will see examples related to that. So again, also for the Cartesian space, we want to choose a parameterization. This time, the vector of the task variable that we call R, it lives in a m-dimensional space where m is, as I said, 6-dimensional, 3-dimensional, and again, the description of the task variable should be unambiguous and minimal. And usually we have, for example, usually we have lower than 6 task, lower than equal to 6. For example, in the case of a scalar robot, you remember it's a robot that has, we saw in the first lecture, has 2 rotational axes followed by 1 prismatic one. Then you can still have the 4th rotational one for the tip, but let's say it's 3 degrees of freedom in this case. In this case, we from a 3-dimensional joint space, can I compute the position orientation of the end effector, for example? That is, our task is 6-dimensional here. Let's say we want to control position and orientation together. Do you think we can do that? Is it possible? Why not?
Because the factor is fixed and I cannot change the orientation.
Because the end effector is fixed, I cannot change the orientation. I repeat the question for the reply for the others. It's true that the rotation cannot be changed. The orientation cannot be changed with the some orientation cannot be changed. Just the orientation about the z-axis can change because these 2 axes are on the z-axis. These 2 joints are on the z-axis. But for example, we cannot change this orientation or this orientation. But this doesn't mean that we cannot compute that. They are fixed. So we cannot affect that, but the structure itself will produce, the direct kinematic will produce certain orientation that will not be dependent on the joint variable, but there will be some numbers there. Okay, so 3 of the 6 variable will be fixed. We can change, for example, the position in the y coordinate. Can we do that on the x and on the x and y? Yes or no? And the factor horizontal positions, can we control them separately? I think we can control it only three things, right? We have 3 degrees of freedom, we can control it on three things. What are these three things? One is the vertical position of the end effector, because this joint is prismatic and is directly affecting the vertical component. That's fine. Okay. Then we have the horizontal component that are linked together, right? Because we don't have a prismatic joint in this direction. So they are constrained to move on a circle, okay? Then we have the orientation, so we can control the orientation around Z. So we can, we have still 3 degrees of freedom, vertical position, orientation about Z, and XY that move on a line. So we have 1 degree of freedom of coupled X and Y. And do you think we can do the inverse kinematics? Can we compute from the position orientation? Can we compute the free angles? Sorry, the free joint variables, the 2 angles and the position of the prismatic joint univocally. I mean, can we map 1-to-1? No, I cannot compute the inverse kinematics in as a 1-to-1 mapping, and so I don't have, because I don't have enough degrees of freedom to place arbitrarily the orientation and position. Some orientation are fixed, so our mapping is not 1-to-1. And if the number of task variable is lower than the number of joints, we are guaranteed that we always are able to place our task variables in a arbitrary way. So we don't have this issue. So in this case, instead M is bigger than N, and we cannot do that. So in a typical industrial case, either M is equal to N, and usually there are 6 degrees of freedom, or industrial robots are 7 degrees of freedom, and still our task is most of time to control position orientation. In this case, we have 1 degree of freedom of redundancy, which is the difference between the task space variable and joint space variable. And for serial manipulators, again, we can say that we have always a solution for the direct kinematics. And this is the mapping. So we call this direct kinematics is function of the joint variables that provides you the task variables. And inverse kinematics is the opposite. We have the task variable as input, and we get the joint variable as output. And again, for the inverse kinematics, we can have either multiple or infinite solutions. We can have no solution at all, or additionally, to compute inverse kinematics, we will always need the forward kinematics expression. The direct kinematics or forward kinematics is the same. They are equivalent. They are synonymous. And instead, the opposite for a parallel manipulator. You know, a parallel manipulator is like one where we have kinematic loop, like a Stewart platform, that the platform that are used, for example, for flight simulators. We have the opposite. We have the direct kinematics is super hard, is difficult, as in the serial manipulator, the inverse kinematics is, while inverse kinematics is easy. So this is just a note. So how do we compute this direct kinematic map that relates joint variables to task variables? We can concatenate the transforms like we did for the rotations. Which transform? Roto translation. So transformation that represent the roto translation of one frame with respect to the other. So first, in a manipulator, we said we can attach a reference frame to each link and joint. We usually number the links from the base, that is link 0, to the end effector, that is link n. And third, we place the joints to connect the links, allowing their relative motions. And this is the sketch of a kinematic tree that represents a robot where we have a mixture of rotational joints and prismatic joints. So the rotational ones are these ones. This one, prismatic is this one. Each joint as associated is single degrees of freedom variable. We don't talk about 2 degrees of freedom joints here. Is not a part of this course, so we assume always joint with 1 degree of freedom, and each variable is associated to each joint. Here we have the prismatic one, and each joint define the relative orientation of the next link with respect to the previous link. And finally, we have the end effector. And you usually place a frame also at the end effector that is a rigid transformation with respect to the last link frame. So we have the joint variables, the task variables are, and position orientation of the frame FE could be an example of task variables. And the idea is that we want to define this transformation between each frame and the next one and concatenate them. This way we are able to go through, express, for example, the position of the end effector in the base frame as a function of the joint variables, because the position of this point will be dependent on the values of all the joints. And to do so, we introduce the concept of roto translations and the concept of homogeneous transforms. That is an operator that implements roto translations. So combines the representation of a position and orientation of a rigid body with respect to another one. And with the term pose, we express both the position and orientation. The concept of position orientation is named with the term pose. So a pose in 3D, as I said, is 3 position parameter, 3 orientation parameters. In 2D, we have 2 position parameter and 1 orientation parameter. So the pose is different according to where we define it. The homogeneous transform are a basic tool to define and derive the direct kinematic from a manipulator, and they are 4x4 matrix that allows to compose these roto translations the same way as we did for rotations. Okay, so we said we work with frames. So let's think about the frame of one link with respect to the previous one. And we have the frame FB. let's think about is attached to the first link, while this FA is a base frame, or this frame could be, I don't know, the end effector frame with a gripper, and I want to map, for example, the reading of a camera attached to the end effector, as we saw in the previous lectures. We want to map this into the base frame. And we see that this frame has a different origin with respect to the frame A. And to define to map this vector P that is defined in the B frame into the A frame, we have two things to do. So first, we have to remember, rotate, map change of coordinates through the matrix ARB to change the coordinates of P into A. And then we need to apply the translation of the true origin of the two frames, because for the rotations the two frames were coincident. In this case, we are considering frames that are can be far apart from each other. So the expression of the vector in A is this vector that represents this plus this one. Everything should be, sorry, this is FA. Everything should be summed up in the same frame. So that's why we do this rotation to the mapping to the A frame, because you don't want to add together pear and apples. And this is called an affine operation. So a multiplication and a sum. And we know that we cannot concatenate this kind of affine operation together as we did for rotation. And a trick that we saw in the lecture on the visual sensor when we were talking about the pinhole model is that we can rewrite this mapping in homogeneous coordinate. We append a scale factor. We choose 1. Okay, so PA expressed in homogeneous coordinate is PA1, and we define this mapping as this matrix. So this is PB expressed in homogeneous coordinate, and we see that if we do blockwise multiplications, we obtain exactly the expression of PA, because we multiply PB times R and 1 times this, and we sum them together, we obtain the same expression, and the one will just remain the one. And this time we have an operator that is linear. So we can do composition of matrix, and see here I said it's the origin of frame B with respect to frame A expressed in frame A. So this is important, is this segment, this vector expressed in frame A, while that is the orientation of frame B with respect to frame A that we saw. And to conclude, we can interpret this homogeneous transform T that describes the position orientation of a frame with respect to another, the position orientation of a frame with respect to another, and we can interpret, as we did for rotation matrix, also as an operator that changes the representation of a geometric vector from a frame to another. And in particular, the homogeneous transform ATB transforms a geometric vector from that is from origin of frame B to the point P into another geometric vector that is from the origin of frame A to a point P. And is a linear relationship. This means I can compose several transforms. And as we did for rotations, we see that we can concatenate multiple rotor translation, just multiplying one after each other. And if you do the product blockwise, you get, in essence, this expression. We can do it. By hand. Yeah, you can if you do this blockwise, you find this element is a product of these two, plus you have 0 here, so this won't count, and you get in essence this element is what is the rotation matrix that represent the orientation of frame C with respect to frame A, while this is just the position, the shift between the frame origin, the origin of frame C with respect to frame A expressed in frame A. And this is exactly the transformation from A to C. So composing the transformation from A to B with the transformation from B to C, we can get the transformation from A to C. Yes, ho finito. Okay, we continue from this point next time, tomorrow. And yeah, I will put online the examples and correct the typo you spot today. And see you tomorrow.